The current race in artificial intelligence is overwhelmingly focused on building a single, massive neural network. The assumption is if one model is scaled up with enough compute and data, it will become an all-knowing engine capable of solving any problem. But looking at computer science history, building a single, unified brain is a fragile architectural bet. A framework proposed half a century ago demonstrates exactly why this unified approach is prone to failure. In 1986, computer scientist Marvin Minsky published The Society of Mind. Minsky argued that a true mind does not operate on one elegant equation. Instead, intelligence emerges from a patchwork society of interacting mechanisms, tiny components that are themselves completely mindless. He realized the messy variety of common-sense reality cannot be handled by a single computational scheme. When an unpredictable edge case occurs, a monolithic system lacks the alternative strategies needed to recover. This shifts the engineering challenge. It's not finding a master algorithm or securing vast raw compute power. It is figuring out how to coordinate hundreds of imperfect, specialized processes. Achieving general intelligence is an organizational achievement. You have to assemble specialized workers so the entire group behaves competently across different contexts. Fast forward to the present day, and the artificial intelligence industry is quietly pivoting. Modern developers using large language models are inadvertently rebuilding Minsky's models piece by piece. While The Society of Mind was published in the 80s, its roots trace back to discussions Minsky had in the 1970s computing landscape at MIT. We are seeing a distinct move away from treating individual foundation models as omniscient engines. Frameworks like CrewAI and AutoGen instead define role-specialized agents that converse and collaborate to accomplish tasks. The critical bottlenecks in these systems are now entirely administrative. Engineers are focused on routing logic, building systems that can persist states, hand off tasks between specialists, and maintain observable traces of the decision-making process. Rather than inventing entirely new paradigms, the industry is rediscovering the physical constraints of cognitive architecture. The need for management layers is a structural requirement of intelligence. Within Minsky's framework, the primary structural division of cognitive work is called an agency. This diagram shows Minsky's hierarchy. High-level goals break down into specific domains, managed by an administrative agent. These managers coordinate subgroups of microagents further down. These microagents are narrow mechanisms, simple detectors, comparators, and search functions. In modern multi-agent LLM systems, the exact same structure emerges. Signals flow into a central orchestrator, deciding where to route data. It dictates flow to specialized planners, researchers, and verifiers, modern equivalents of microagents. Below, a shared memory layer feeds context back to the active agents. They operate as strict policies and routing constraints. An individual agent is smart only in the specific sense of completing a very small job reliably. Modern LLM instances possess broad language competence, unlike the 1980s microprocesses. However, the structural necessity for an administrative layer to arbitrate between them remains identical. If you string together competent LLMs without hierarchical governance, the system falls apart. Without an orchestrator, you encounter goal drift, brittle tool use, and hallucination, making the administrative layer mandatory. When assembling a society of specialized AI agents, you encounter internal contradiction. Different agents will propose completely different solutions to the exact same input. In traditional software design, conflicting data outputs are treated as fatal errors. The engineering reflex is to immediately suppress the contradiction to maintain stability. In the early 1970s at the Massachusetts Institute of Technology, Minsky collaborated with computer scientist Seymour Papert to study how these conflicting heuristics actually operate. Their work led to Papert's principle. This concept reveals that internal conflict is actually a feature, a structural driver forcing the system to evolve new administrative control layers to resolve disputes. According to this principle, acquiring new skills is insufficient for growth.
The system must acquire new administrative ways to arbitrate between the skills it already possesses. This maps directly onto modern multi-agent debate patterns. Developers intentionally build a critic agent whose entire structural purpose is to challenge the output of an executor agent. Having multiple approaches is structurally mandated. A messy real-world situation has distinct facets, and different heuristics are required to process each one accurately. You achieve system robustness by adding middle managers and clear escalation paths. By exploiting internal conflict rather than forcing a unified consensus, the system creates a far more rigorous final output. The standard assumption in AI is that memory is an archival retrieval system. We treat it as pulling a static, perfect text transcript of a past event. Minsky proposed an entirely different mechanism called the K-line or K-node. It serves as a functional theory of how a society of computing processes actually remembers information. Remembering isn't retrieving a static record. It's the active reinstatement of the specific configuration of agents that successfully solved a past problem. Excitatory connections wake up previously active agents. This compositional process, the K recursion principle, builds new memories directly on top of currently active K nodes. Translate K-line mechanics into today's engineering, and they describe advanced retrieval-augmented generation, or RAG. This technique retrieves external data from a vector database to ground the AI's responses in specific facts. A retrieved episode executes specific tools, enforces operational constraints, and triggers targeted sub-agent activations instead of simply returning text. Without dynamic sensitivity, systems fall into the trap of over-anchoring. Merely dumping old text into the context window locks the system into stale assumptions, ignoring the nuances of the present problem. This makes K-lines a form of proto-orchestration memory. They encode instructions on how to re-enter a productive working configuration, rather than just stating what happened last time. True agentic memory loads the exact computational state required to solve the task at hand. Recreating successful configurations is the modern equivalent of the K-line. These structural lessons point directly toward the AI industry's most heavily debated goal, artificial general intelligence, or AGI. AGI refers to a theoretical system that can understand, learn, and apply intelligence across a wide range of tasks at or above a human level. Minsky heavily criticized the use of suitcase words. These are terms that bundle many heterogeneous, highly complex processes under one familiar yet misleading label. Treating intelligence as a single property creates a dangerous illusion. It leads to the assumption that true artificial general intelligence will magically emerge simply by piling on more raw computing power and larger datasets. AGI is the ultimate suitcase word. We pack it with distinct, separate capabilities like transfer learning, long-horizon task coherence, scientific creativity, and complex tool use. Treating AGI as an unanalyzable monolith forces us into a dead end. It encourages the false belief that general intelligence will arrive as a single, sudden threshold event, where a machine simply wakes up. Minsky's solution was to de-suitcase the term. We must unpack the word, specify the exact sub-capabilities required, and build the dedicated routing mechanisms needed to coordinate them. General intelligence should not be assessed by a single benchmark score. It is defined by a system's organizational capacity to route among diverse representations, invoke alternative strategies when stuck, and recover from localized failures. This completely reframes the current debate between single-agent and multi-agent architectures. A robust mind structurally requires multiple ways to think and dedicated mechanisms to arbitrate between those thoughts. The most durable advances in the coming years will not come from clever new prompting tricks. They will come from heavy engineering investments in organizational infrastructure, state persistence, and system observability. To build systems capable of surviving the unpredictable variety of the real world, the physical laws of computer architecture force our hand. We cannot build algorithmic gods. We have to build resilient societies.